All right, welcome back. Let's do some polymorphism. So let's jump right into it. Logistics. Don't forget the problem set 1 deadline tonight. We have office hours throughout the day today. We have Jack has office hours right after lecture today, and Miriam's still bold enough to go right before the deadline. So if you have your last minute questions, feel free to ask them there. And the much demanded, requested tracing practice. I posted a we'll fill in each solution. Shouldn't be too long for the solutions, but we'll fill in the solutions once you've had a chance to work on the traces. So this is basically a sample midterm or final exam. This could very well have been one of those exams, either the midterm or final. They both have the same exact structure with the same question types. There obviously be slight differences between them, and the questions will be completely different. But this is what it's going to look like. So the best thing you can do for practice is to set up a time where you have 2.5 hours to sit down and do tracing practice, and try to take this as if it were an exam. Just 2.5 hours, do all 4 traces, and then when we post the solutions, or if we already posted the solutions by the time you do it, go through the solutions after that 2.5 hours, and then check all your work, see what you did, anything you did wrong, review it, make sure you know what's up. If you can't figure out what exactly you did wrong or why the solution is the way that it is, come to office hours, ask us questions, and we'll get you there. But here's the effectively a sample exam. This is the we're not going to add more practice problems onto this, but this should be, I would assume this will be sufficient to be able to do a full practice exam. So much requested, there it is. I feel like I had another thing to say about that, but I don't think so. I think that was something for the TAs. I had to tell the TAs. The one thing. So the DS2 does involve trees. I have argued, and I will continue to argue, that you could do the tree traversal right now. Like, there's nothing new or special that I have to talk about in terms of tracing concepts when we talk about trees. It's recursion. It is recursion where there are 2 recursive calls in each method. Call. They're making 2 more method calls with recursion. So I'll talk about that when we do the binary tree traversal. But that's not a new concept. Like, nothing. I'm not going to hit you with anything brand new with that. If you understand tracing, everything we talked about up until this point, you can do tree tracing. You don't have to see a tree trace. In fact, I'm only going to show 1 tree trace during this lecture because I just don't have anything to say about it. Like, you should already, if you've been studying everything up until this point, there's nothing new really to say about trees except just emphasizing how multiple recursive calls work, which is the same as multiple method calls from a method, which admittedly we don't do all that much, but it is the only kind of new thing with trees. So if you do want to wait for the trees lecture before you sit down and do that as an exam, if that's the way you want to study, you're welcome to do that. Obviously, you can study however you want. Most students, especially the ones who don't watch lecture live, so the ones who aren't hearing me right now, maybe you're watching the video later or whatever, most students won't even do the practice. They'll just go into the midterm, fail it, and then take the final. But those of you who are actually listening to me, I do recommend doing it as an exam. Of course, study however you want. Some students like to wait till the solutions are out and then do the traces while referring to the solutions. I don't think that's the best way to study because that's basically what I give you in a lecture. You can follow along during a trace in lecture and just always see what I'm doing. I don't think that's super helpful because you get enough of that already. But if that's how you want to do it, whatever. But that's our plan. We'll get the solutions up to those ones, and you can study how you want to study. But that's the structure. That's what's going on with that. I think that's all the announcements I want to say. I already talked about the deadline. After Tuesday's lecture, you already have everything you need for problem set 2. You can get started with that. And I guess the usual summer goes fast. We are halfway through the content. I've done half of the lecturing that I'm going to do for the entire summer. After today, it'll be up to 60%. It's only 10 lectures, so it goes very quick. After next week, it'll be at 80%. And once I find time to record the async lecture, it's going to be at 90%. Graphs is the only thing left after next week and the async lecture. So, yeah, it goes fast. Make sure you're keeping up to date. If you haven't been taking this summer course very seriously and giving it most of your free time during these weeks until you finish the assignments at least, then you're far behind. But those of you hearing me say this at a reasonable time, that's not going to apply to you anyway. You're all keeping up to date with things and are ready to learn polymorphism, so let's just do it. Let's just learn polymorphism. Okay, and as always, I'll be watching chat, so so make sure you get your questions in chat. Oh man, why are there so many emojis? Just give me the common ones. And let me know if you have any questions in chat. Now, how do I get rid of this? Usually don't use this interface for chat, so, well, now my emoji menu's always up. Whatever. So, let's talk about polymorphism. And I think polymorphism, in my opinion, polymorphism is the biggest payoff of setting up inheritance. Last time we talked about inheritance without the context of polymorphism, and I can still sell inheritance. It's to reduce duplicate code when you have a lot of classes that do similar things. You have a lot of common functionality in weapon and health potion and bow and arrow and any other game item that you want to add to your game. Abstract out, factor out all of the common functionality from all those classes, put them in a common superclass, and then extend that class. So now every object of every one of those types just automatically gets all the functionality in that superclass. So it can reduce duplicate code and let you reuse that code very easily across classes. That's a pretty good selling point, but really where the huge payoff is with polymorphism. So let's make sure we know what inheritance is first so we can get our polymorphism going. So inheritance is where we can inherit all of the state and behavior from another class. So when weapon extends game item, weapon gets all of the instance variables and methods from the game item class, almost as though it were typed directly in the weapon class. And we can have multiple classes extend the same class. So weapon and health potion both get all the state and behavior of game item. So if we create an object of type health potion or weapon, we get all the instance variables of the respective class and all the instance variables of the class that it extends. So those objects also get X location and Y location. Just because super constructors are so important, I'll get my face out of the way here. And you get all of the methods. So we get the super constructor, which must be called, and all of the methods. So weapon and health potion both get this use method. So health potion, if we call the use method, we look in the health potion class. We don't find a use method, so we continue our search to the super class. Find the use method here, and that's what's called. Weapon overrode that use method, so it said, yeah, I know I inherited this use method, but I don't like it. I'm going to replace it with my own definition. So it overrode use. So when we call use from an object of type weapon, that object says, oh, I have a use method right here, finds the use method, calls this, and does not even look at the superclass for a definition that was inherited. It just finds it right here and calls it and stops the search right there. And your super constructors are always, always called from the child class constructors. Here they're both explicit, but even if the keyword super and the constructor call isn't here in the code, it still does happen. The only way that can happen is if the superclass has a constructor with no parameters. That constructor will still be called even if the code isn't here for it. Here they're explicit. The superconstructor is explicitly called. Very hard to miss that in your traces. Very hard to miss your superconstructors. And I do like to do this. I'll do this on the exams, that they will be explicit calls, so there's no hidden gotcha questions. And then if you miss your superconstructor calls, then I really know you haven't paid any attention, which again won't be anybody who's hearing my voice. You're all going to do great. You're not going to miss your superconstructor calls. You're going to get it on the midterm and not even have to worry about the final exam. There will be students who have probably not watched a lecture yet, might not watch a lecture before the midterm, and then not have their superconstructor calls, and hopefully study before the final and still somehow squeak by with a C in the class or something, but more likely we'll have to retake the course. Don't be one of them. Make sure you get your superconstructor calls. They'll be explicit, not trying to trick you, just trying to make sure you understand what superconstructor calls are. Very important concept to understand when it comes to inheritance. So that's all inheritance, and that's what we know of inheritance. That's all inheritance. And I want to explain what these relationships are, like a new way of describing these relationships with inheritance. So we saw weapon extends game item, that's explicit. Game item doesn't explicitly extend anything, so it implicitly extends the object class. And weapon indirectly also extends the object class. So it gets the state and behavior of the game item class that we talked about at length last time. But weapon also gets all the state and behavior of the object class, which we talked about a bit last time. We talked about toString in this, but I want to make this very clear that weapon inherits all the state and behavior of game item, and weapon inherits all the state and behavior from the object class. So weapon has all of the state and behavior of all three of these classes, almost as though you took all the code from object and game item and pasted it right into the weapon class, but without having to paste. So when we have multiple classes inheriting from the same superclass, we don't have to paste that code twice. We just type extends, and we're done. Two words: extends game item, done. Even if okay. And there's another way of phrasing this, is that this is an is-a relationship. In a very real sense, if a class extends another class, it is that class. It is an object of that type. So when we say weapon extends game item, yeah, we get all the state and behavior, like we've said a bunch of times. But weapon also is a game item. So if weapon extends game item, it is a game item. This is very similar to the fact that all squares are rectangles. All squares have all of the properties of rectangles, and then squares also add more properties to that. We're doing kind of the same thing here. Obviously, we're not in geometry, we're in OOP, but it's the same idea. Weapon has all of the state and behavior of game items, and then also adds more state and behavior specific to weapons. So a weapon behaves, like if you take a weapon and try to treat it like a game item, it's going to do everything that a game item does, and then more things. So we take this to the extreme and say, yeah, a weapon is a game item. And since weapon indirectly extends object, we can say weapon is an object also. So weapon is a weapon, that's obvious, but weapon is a game item, and weapon is an object. So that we have this is a relationship. If you extend a class, you are that class. A weapon really is a game item. Which makes sense intuitively too. If you see a weapon in the game, you say, yep, that's a weapon. You can also say, hey, there's a game item on the ground. The end user, the player, probably wouldn't word it like that, but it is accurate. Like, that is an item in the game. That item in the game happens to be a weapon, but it is a game item as well. So polymorphism means, what polymorphism does for us is that when an object is a type, if an object is a type, it can be stored in variables of that type. One of the few slides I'll read verbatim. If an object is a type, so if it has that is a relationship, that extends relationship, that inheritance relationship with another type, its objects can be stored in variables of that type. This is polymorphism. I emphasize this so much because there's always a lot of confusion between what is inheritance and what is polymorphism. This is polymorphism, everything else is inheritance. So this is what polymorphism is, and the obligatory polymorphism slide. Poly means many, morph means form, so polymorphism means many forms. Your objects can have many different forms. A weapon has 3 different forms it can take. It can act as a weapon, it can act as a game item, and it can act as an object. Meaning it can be stored in variables of any of those 3 types. Which is pretty freaking cool. For now, you'll have to trust me. We will get to why that's so cool and why that's so important. But let's talk about some mechanics of that. And actually, I'm going to start with one of the big limitations of polymorphism. That's how strong polymorphism is. I'm going to lead with its downside, and the upside is still going to sell it so much that you'll fall in love with polymorphism. Probably not today, but eventually you'll appreciate the power that polymorphism provides us. So all 3 of these lines are legal. This is all valid code. This program compiles, it runs, everything is fine. A weapon can be assigned to variables of type weapon. That's fine. That's what we've done all semester. This is what I've always said all semester. Java is strongly typed. If you have an object of a type or a value of a type, in the case of primitives, it can only be stored in variables of that type. And variables of this type can only store, values of that type, or in this case, a reference to an object of that type. But then the next line works. Here, the type does not match the object type. The variable type does not match the object type. This is still a perfectly good assignment because a weapon, in a very real sense, is a game item. To the extent that a game item variable can store a weapon object or a reference to a weapon object. I won't always say reference to, but that just to emphasize that is what's happening here. A game item variable can store a weapon because a weapon is a game item. A weapon is that type. It is the game item type. So this is a valid assignment. You can do this. You can do this all day. Perfectly fine thing to do. And you can go to the other type. Weapon has 3 different types, has many forms, has 3 different forms. It can also be stored in variables of type object. So if you wanted to store your weapon in a variable of type object, you're more than welcome to do that. You can just do that. Because of polymorphism, polymorphism says you're allowed to do that. You extended object, you can store your object in variables of type object. A perfectly fine thing to do. So if an object is a type, if it inherits from that type either directly or indirectly, it can be stored in variables of that type. That's polymorphism. That's what we're talking about. Okay, so what does this mean? I'll table the question of why the hell we would even want to do this, because it seems like a dumb thing to do on the surface. And in fact, in this, and I'll explain this as we get more and more understanding of this, but this code as written, these second 2 lines, the second and third line, you would never actually do this. Trust me, this is useful. We'll get to it, but you would never actually write these 2 lines, these second 2 lines, the last 2 lines. But there's one big, and because of this one big implication. So if you store a variable, if you store an object in a variable of a different type, of one of its super types, you're actually limiting yourself on what you can do with that variable and with that object. So this is our first limitation, really our only limitation with polymorphism, is that you can only call methods that are known to the variable type. So when you try to call a method, if the method definition is not known to the variable type, that method cannot be called. It's not allowed. You can't do it. Not allowed to do it. So when I have weapon 1, weapon 2, weapon 3 of type weapon, game item, object respectively, and I want to call get damage, this is a method, recall this is a method that we defined in the weapon class and not in the game item class, and certainly it's not in the object class. For the Java's object class to have a get damage method would be pretty silly. To make sure that every object in Java has a get damage method. It's not going to apply to the vast majority of classes that exist. But it does exist in the weapon class. The weapon class knows about it. So when I try to call this get damage from weapon 1, this is perfectly fine. Weapon 1 is a variable of type weapon. Weapon class knows about the get damage method. Perfectly valid method call. Weapon2.getDamage doesn't compile. If I comment in this line, program doesn't compile, can't run it, everything breaks. So we can't do this. This is not allowed because weapon 2 is of type game item, and the game item class doesn't know anything about this get damage method. It has no idea what this method is. It's never heard of it. Because inheritance only works one way. Weapon knows all about the game item class, but game item has no idea about the weapon class. Nobody gave game item a heads up and said, hey, by the way, there's this class called weapon that inherits all of your state and behavior. Game item has no idea weapon exists. So game item has no idea the get damage method exists. So from weapon 2, we cannot call get damage because the variable type does not know anything about it. Can you do some tracing with super... I assume you mean constructor. Super constructor to help me understand how it looks like in tracing. Yes. So the trace that's coming up will have super constructor calls, and the traces from Tuesday. We did multiple traces on Tuesday that have super constructor calls. If you want to rewatch those and get more practice with those. But we are headed to a trace today. We're going to do this big old trace. It's a pretty big, pretty long trace. It's a full lecture in the regular semester, so 50 minutes of today. And we are going to create a new weapon and a new potion. Weapon and potion will both extend game item, so we'll see the super constructor calls in today's trace. So that is upcoming. I'll stay in order here, but we will get more examples of super constructor calls today. And then certainly from weapon 3 of type object, object has no idea that game item extends it, much less weapon, has no idea about any of this stuff. It does not know about the get damage method, so we cannot call get damage from the variable of type object. Even though weapon 3 does store a reference to a weapon object. This is the crazy part, because the weapon object being referred to by the variable weapon 3 has a get damage method. Like, it has a get damage method. It exists. It's there, ready to be called. We just can't call it because we stored it in a variable of type object. So the variable type restricts what we can do. So this is a pretty big downside. The variable type restricts what we can do because we're restricted to whatever's known to the variable type. Kind of big downside. Very important to know this interaction. But say the use method. Say we want to call the use method. Recall the use method was defined in the game item class. So we can call use from our game item variable. We can call that here, and we can call it from the weapon variable. Both of these types, weapon and game item, know about the use method. So we're allowed to call those. It's perfectly fine. But weapon 3 still doesn't. So the variable type object has no idea there's a use method that takes a reference to a player, doesn't know about it, can't call it, doesn't compile, doesn't work. Even though that method does exist in the object that it's referring to, still can't call it. Still can't do it, not allowed. Java won't let you do this. Some languages will, by the way. and it'll, if the method doesn't exist, it'll just crash. But here the method does exist and it would call it. Java, not so much. Java's not going to do that. Because Java's strongly typed, it's not going to let you do that because the method might not exist. But what happens when the method is called? So I've emphasized this in every trace that we've done just to make sure that we don't have to really learn anything new with polymorphism, is what happens when the method is actually called. So when the use method is called here, recall that GameItem defined the use method, and then the weapon class overrode the use method and did its own thing. So weapon overrode GameItem, the GameItem use method that it inherited. So when I call use from weapon 1, it should be pretty clear that it's going to be the weapon method that's called. We've done that a whole bunch of times. But once the variable type does not match the object type, which method is going to be called? And the answer is the same thing. It's still going to be the weapon class's use method that's called. The one that overrode the inherited one is still going to be called, because which method is called only depends on the object type. So what's actually being referred to by that variable. So the variable type determines which methods are allowed to be called. But once the method is actually called, it's the same thing we've always been doing. It's business as usual. You look at the type of the object on the heap, go to the class matching that type, and then look for the method, go through your progressions if necessary, and that's the method that's called. The variable type doesn't matter when the method is being called. It only matters when determining if the method is allowed to be called. And I'll repeat this a whole bunch of times today, especially when we go through the trace, is that the variable type determines if the method is allowed to be called, but when the method is called, it's the object type being referred to, which in all three of these variables is weapon. It's the object type that determines what's actually going to happen when that method is called and which version of that method is going to be called. And we can take this all the way to toString. ToString can be called from all three variables, and no matter what we did with the toString method, if GameItem overrides it, if weapon overrides it, if both weapon and GameItem override it, or if neither of them override, no matter what happens with the overrides, all three of these method calls will do the same thing. It'll be the same version of toString that's called every single time. Because we'll always start in the class matching the object type. So all three of these calls, regardless of the variable type just says, yeah, you're allowed to call this because object knows about toString, GameItem knows about toString, weapon knows about toString. But once the method is actually called, we go to the object type, which is weapon in all three cases. So we go to the weapon class, look for a toString method. If we find it, we call it. If we don't find it, we continue on to the GameItem class, look for a toString method. If we find it, call it. If we don't find it, continue on to the object class and then call that default toString method that we should override because it's kind of useless. So the variable determines if a method can be called, and the object type determines what happens when the method is called, which method is called. So that's the big downside of polymorphism, is you restrict yourself. Actually, I want to go back to the slide. So you restrict yourself on what you can do. So my big question is, why the hell would you ever do this? GameItem weapon2 equals new weapon. What we've done is restrict ourselves. We said we can't call get damage or any other methods we add to the weapon class. So why would we do that? And the answer, as shown on screen right now, the answer is don't do that. Just store your weapon in a variable type weapon that gives you maximum options, maximum flexibility. You can call anything that class can do. Anything that object can do, you're allowed to do through this variable. Don't restrict yourself artificially. Like that's kind of just silly. So for weapon 1, we would be able to use the method of weapon, and weapon 2, we would be able to use the use method of GameItem. The method call is going to be the same. So weapon1.use, weapon2.use. These methods do the same exact thing. You cannot access, you can't break inheritance like we were doing last. Not that we didn't break inheritance last time, but just like last time, how we couldn't break inheritance. Like if the weapon class overrides the use method, you can no longer access game items use method. Period. Like you cannot call it. So even though weapon 2 is a variable of type game item, we still can't access the game item use method. That's not how it works. But we can call the use method. But what happens when the method is called still depends on the type of the object, which is weapon. So we always still start in the weapon class, find the use method in the weapon class that's overriding the game item use method, and we still call the weapon use method. We still have no way through polymorphism or any other means to access a method that's already been overridden. It can never happen in any way. The variable type is just determining if the method is allowed to be called, but what happens is always going to be the same. These two methods will do the same exact thing. These three methods will do the same exact thing because we're always starting in the object type. And the object type in this example is all weapon. Okay, so if you would never do this, though, why are we learning it? Why is this a thing? Why is this a core fundamental computer science topic that every computer scientist needs to know, every software engineer needs to know? You'll get asked this in job interviews. Maybe this specific topic doesn't come up, but a lot of job interviews, they'll ask about polymorphism. Why is this such an important topic if all it does is restrict what you can do? And the benefit of polymorphism, the reason we love this so much, and the reason it makes so much code so much easier, and in fact, I'll go as far as to say makes programs even feasible to write. Certain programs with, depending on how you're structuring it, certain programs would be at least practically, not literally, but practically impossible to write without polymorphism, is because polymorphism can be used to simplify other classes. You don't use polymorphism to simplify the class that you're using. You use polymorphism to simplify other classes that use that class. And it might have sounded a little weird, especially because we have a use method we're talking about. But consider the player class that wants to have a method called use. So far, all of our use methods have been in the item classes themselves, weapon and health potion. But what we really want is a player to be able to use items. We want the player to be able to say, I want to use an item, I want to use some item. And then we're going to call that items use method, pass a reference to the player that's using that item, that called use item. This is a reference to the player that's using that item, and call that items use method there. But we want the player to be able to use an item. That's the ultimate goal of the game, really. So the player needs a method that's going to use an item. But we would need a use method for every single item type. That's a problem. We would need use weapon that takes a weapon, use health potion that takes a health potion, use bow and arrow that takes a bow and arrow, use mana potion that takes a mana potion, use sword that uses a sword. You're going to need a use method for every single item in your game. And that gets tedious. That's a whole bunch of use methods, one for every single one. That's going to be very painful. Not too much when, okay, I copy and paste this method every time I add a new game item to my game. It's not that big of a deal. I changed the name of it. I changed the type that it takes. It's not a huge deal. That's still a problem. I still wouldn't like that in my code. But somewhere else in your code, there's some system that's calling those methods, and that system is going to need duplicates as well. Whatever your inventory management system is, that's going to have to call each use method and call the right one for whatever item is currently being used. That's going to get painful quick once this cascades through your entire program, where every piece of code in your program that works with a game item needs to be duplicated for the number of game items that you have. That is where things get really painful, and this is where polymorphism comes in. Polymorphism says, screw all that, just write one method and take a game item. Now I don't care if you have 50,000 game item types in your game. You write one method and it handles all of them. Done. That's it. Any method that the inventory management code that's going to handle everything, it just works with game items. It doesn't care if they're bow and arrows or swords or health potions. It doesn't care. It just cares, hey, is this thing a game item? Does it extend game item? If it extends game item, my code works. Easy. Done deal. If it doesn't extend game item, then it doesn't work. So this is the strength of polymorphism. You simplify other classes. You write a use item method that takes any game item. This method can be called with weapons and health potions and any other game item that we come up with. It can be used with all of those, even game items that don't exist at the time that we write this method. We come up with a new game item later in the future. We don't have to update the player class because the player class is just working with game items, not specific item types. It just works with any game item. Anything that extends game items works with this method. This makes it so much easier to write our code. Oh, this code. We had this player extends game item so player could have a position in the game. I don't like that. Pretend player doesn't extend game item. Just such a silly thing Paul and I decided to do when we wrote these examples. I gotta update that sometime. But player being a game item doesn't make sense. It kind of makes sense why we did it, but doesn't make sense intuitively. So this method works for any game item that we ever come up with. But there's more. Remember forgot I had a whole nother, actually, yeah, I'm glad I do have this slide. So like I said on the other slide, we would never do game item equals new weapon. We would never do this as written here, but we'll have the same exact logic just spread across a parameter being assigned to an argument. So we have game item equals some weapon somewhere else in our code, but that's across a use item method call. That's where we will have these assignments. We won't have them in line in a local variable, but we will have them across method calls. That's where they're powerful. That's where we have objects of one type being stored in variables of another type. It's so we can write methods that work with the super type, and that method can be called with any child type of that type. That's the power of polymorphism, when it's across method calls. And there is more. Well, you know what? I do want to talk about this too. Let me circle back to that because I want to say what the more thing is. I'm just eager to talk about data structures here. So there's more. Remember data structures? Data structures have to have a type. You have to give it a type parameter, and data structures can only store objects of that type. But now that we have polymorphism, that type can be one of the super types, a common super type of our classes. So we can also have an array list of game items. So now we can have a player inventory, kind of have that inventory management system that I was mentioning. We can put that right in the player class, have an array list of game items, and that's the player's inventory. I can have methods that add items to my inventory, and I can have methods that work with that inventory. Here, just to try to keep this as concise as possible on the slide, and also the eventual memory diagram where we're going to trace through all this code. We had a simple use all inventory method, inventory items. You wouldn't really want this method if you're playing this game. If your only option is to use everything in your inventory, it's kind of an awkward mechanic to have in a game. But we can have an example with just 4 lines of code here in the method. So using all inventory items, we can iterate over our inventory and then call the use method on every single item. So when we use these super types, when we use these variables of type game item, because now everything in the player class, like a player's not going to know what a health potion is anymore. It's only going to know about game items. So whenever we're working with game items, when we're calling use item, pick up item, use all inventory items, storing things in our inventory, it's all game item type, meaning that we can only call methods that are known to the game item class. That's where the restriction becomes really important, because we can't say item.getDamage here. We can't say item.getIncrease. Did we have a getter for that? I don't know if we wrote a getter method for that. But we can't write any code that's specific to health potions or weapons. We have to write code that is known to the game item class, but the behavior we get will be weapon and health potions specific. So when we call use, if I'm using a health potion, I still get the health potions use method, and I still increase my health. Very important, we get the health potion behavior here. But what makes this a valid method call is the fact that the game item class knows about the use method that takes a reference to a player. So we can only work with game item functionality, but the functionality methods known to the game item class, but the functionality we get from those methods, the behavior we get from those methods, is still specific to each child type. So the restriction that we have that we can only call methods known to the super type doesn't actually become that big of a restriction in practice. If you ever have a situation where you're like, man, I really want to get damage, I would really want to call get damage here, but I'm working with game items. You have two choices: either change your variables to weapons and have that code be specific to weapons. So if it's, if you're calling get damage, maybe you're equipping that weapon and using it to strike an enemy or something, strike a monster or whatever. Well, in that case, maybe it shouldn't be abstracted all the way to game item. Maybe that should be a weapon variable at that point. Kind of asking yourself, why do I want to call this method that's specific to another class? Or if you're like, no, I really want to work in the world of game items, I have to be working with game items here, you take the get damage method and move it to the game item class. Now game item knows about the get damage method. You can have it always return 0 in every other class, and then for the weapon class, have it return something. That's usually, in practice, it's usually what ends up happening. If there's a method you really need to call, you just move it to the superclass. If you need to call it from a superclass variable, it's probably an indicator that it belongs in the superclass class. It belongs in the superclass. So you move that method up, and now all of your game items have that method, and then you can call it where you want. So the restriction, it is a restriction, but you control all the code. You can just move the methods, just move them around. And this is where we'll circle back to this after the memory diagram too, but this is where abstract methods are really handy, because I keep saying the method has to be known to the superclass. I'm very careful with my wording there. It has to be known to the superclass. Known doesn't mean the method has to completely, fully exist in the superclass. It can be abstract. And this is why we would use abstract methods. I want my superclass to know a method exists, so I can call that method through my variables of that type. But at the same time, I don't have a default behavior that I want to give those types. I don't have any default behavior that's interesting to me. So when that's the case, I'll give it an abstract method. I'll say, okay, now this type knows about the method. It doesn't have any meaningful implementation or behavior to give to this method, but I do want it to know about it, so I can call that method through variables of that type. And the actual object stored in that variable will be the concrete class. Oh, I don't think I defined that last time. Concrete class is a class that's not abstract. So pretty much most every class that we've seen all semester would be considered concrete classes. So the concrete classes, we don't know what they're going to be, but we know that they will have implemented the abstract method, because if they hadn't, we wouldn't have been able to have an object of that type. We wouldn't have our hands on a reference to an object of this type if it hadn't, at some point along the way, through inheritance and overrides and everything, it had to have implemented that method. That had to have happened along the way. So we know the method exists. We have no idea what it'll do, but we know that it does have to exist. Oh, I did put the slides right here. Sorry about that. So with abstract, some of these slides are duplicated from the last lecture. But yeah, I forgot I duplicated them here because I knew I wanted to say it, and I did say it. But there's no need to go through all of the slides again. But so this is where it really shines. You can call abstract methods using polymorphism. If I have a variable of type game item, I can call the use method because the game item abstract class in this case knows that the use method exists. Therefore, through game item variables, I'm allowed to call the use method. I don't know what it's going to do. That depends on the child classes and the overrides, but I know it will exist and that it will do something, hopefully something useful, but it'll do something. It will have a definition. I mean, I guess it doesn't have to do something. The definition could be open brace, close brace in this case because it's return type void. But it will have a definition. I can guarantee that, or else we wouldn't have an object of that type. Same with interfaces. So interfaces, this is where they're handy, is if I have a variable of type comparator, I don't know what it's going to do, but I know it has a method called compare that takes two objects of the type parameter type and returns a Boolean. I know that's going to exist. So I can have variables of type comparator of integer, which we'll do towards the end of this lecture, of comparator of integer, and as long as I have an object of a type that implements that interface while specifying the type parameter of integer, what you can do, you can specify type parameters while extending a class. You can have a class that extends, oh, actually I don't think you can, but I'll use this as an example anyway. You can have a class that extends array list of string and have a class that is an array list of strings and then modify it there. Aside from comparators, we won't use that feature in 116. The reason I say I don't think that's actually possible, actually, let's take a small detour because I do want to know right now. This is player with inventory, array list. Oh, you can do it. So some classes are declared as final. Is it a waste of time to try to find one? Let's try to find one. Try to find one quickly. I know math is. That's less interesting because you can't instantiate math anyway. Oh, but you could extend it if it weren't final. This is taking more time than it's worth. Let me just go to the math class. So the math class is defined as final. If you have a final class, that means you can't extend it. That's just a way of saying you're not allowed to extend this class. I don't know. I don't like making any classes final because it's just restricting other developers, but there are a lot of built-in classes in Java that are final, the math class being one of them. I guess they're worried that you might instantiate the math class. If we extend math and then write our own constructor for the class that we wrote, then we could create an object of that type. I don't know why they're so against us creating objects of the math type. It's not useful, but like you don't have to try so hard to stop us. Sometimes it might be helpful to have my math class and write some more methods, but I mean no, but like final is just so final. Polymorphism. Let me grab this trace in my clipboard because that's where we're headed pretty soon. I have two polymorphism ones. Oh, and they both disappeared. Oh man, I'm all over the place right now. Let me just make sure that was the last slide I needed. Yep. Let's go back to the website. Grab the next set of slides, which shouldn't have much on it. Do I have anything on this? Yeah, I just go right to the memory diagram. The I do. Yeah, it is just a memory diagram. I confuse myself a little in the summer because when I prep, I'm thinking of one whole lecture, and then I do forget where the boundaries are between the three from the regular semester. Because I know we go through all those slides and then go through the whole trace, but where the boundary is. So this is the trace that we want to go through right now. The reason I do want to go to the slides real quick is this is the only time we'll have all of the code on screen at once. I'm quite certain when we go to the tracing tool, I won't be able to fit all of this on screen without scrolling up and down a lot. So let's go through this code and just talk about what we're expecting to see during this trace. Well, we can see everything all at once. So we have the main method creating a new player. The player is going to have a few instance variables. We don't have an explicit constructor, which, did we even talk about that yet? I don't think I talked about that yet. It's a big thing right after this trace. I'll emphasize it a lot, but yeah, this is the first time we'll see it. I think it naturally comes up a different way in the regular semester, but I forget how. Oh well. But anyway, so we have no explicit constructor. I'll just explain it right now. It's not that big of a deal. We have no explicit constructor right here. If you don't write a constructor for the class, you know what, now that I say it, this did come up earlier, but in the same way that I'm doing right now, just as a one-off note, not as like official slide content. If you write a class and don't provide a constructor, you get what's called the default constructor for free. You don't have to do anything. You just automatically get a constructor. That constructor takes no parameters and has no body. Well, it has a body, but the body's empty. So it's public player. So this is just like we have public player, open paren, open brace, close brace. That's the constructor you get for free if you don't write a constructor. So like for problem set 0, I used this as the example last time. Problem set 0, we don't write any constructor. It's a collection of static methods, so there's no need for a constructor. You call your static methods by doing problem set 0 dot whatever. So there's no need to instantiate it. We didn't create a constructor. We didn't talk about constructors at that point. But we did still get the default constructor for free. So you can still say new problem set 0, open paren, close paren with the empty argument list. You can do that, and you have an object of type problem set 0. You're allowed to do that even though you didn't write a constructor. That's why math has a private constructor instead of not writing a constructor at all. If it didn't write a constructor at all, it does get a public default constructor, and you would be able to say new math, which again, like, who cares if people write new math? It's a dumb thing to do, but like, what's it gonna hurt? But they really don't want us to instantiate the math class. You still can, by the way, using something called reflection, but I'm not going down that rabbit hole. Actually, I will a little bit, because this can be important. If you're out there programming, the keyword private isn't made for security reasons. There's no security behind the keyword private, because there are ways to undo the keyword private. To take a private instance variable from some other class, you could import player and modify the player class to change private instance variables to public and then still modify them directly. So it doesn't prevent people from modifying them directly. It's more of a heads up to your fellow developers that says, hey, you really shouldn't modify these variables because you're probably going to break something. But if somebody wants to be malicious, they can still change those variables. Like, you do have to trust your fellow developers on a project. They can modify your private instance variables, call your private methods. They have the power to do that. There's nothing stopping them. So never say, if you're in a job interview and somebody's like, why do we use access modifiers like private? Do not say for security. That's not the reason. It's for communication with your other developers, with your teammates, with your coworkers. It's for communication purposes. Anyway, so you get the default constructor for free, so we can still say new player. We have to give it an empty argument list because we have an empty parameter list, and then the constructor just doesn't do anything. And then all of my instance variables I'm defining inline, so I'm still initializing all my instance variables, but the constructor doesn't do anything, and the constructor doesn't have any parameters. So this is a case where none of the instance variables are in the constructor stack frame. that I emphasize each time we see a constructor. Most times we see a constructor anyway. So we create a player, create a weapon and a potion. That's just like we did last time. We did this multiple times. We'll do it again today. The one new thing here is that we also implement an interface. So we extend weapon extends game item. That's the stuff we've seen last time. But we also implement a usable interface that has a method named use. And one of my big punchlines for interfaces in the trace is that if you have a trace and you see an interface, if you see implements some interface in a trace, just ignore it. Completely ignore that the interface exists, because it will not affect your trace in any way, shape, or form. In fact, it's the same thing with polymorphism. Potion being stored in a variable type usable does not change your trace at all. The difference that polymorphism makes on your traces beyond inheritance, after everything with inheritance, what polymorphism adds to your traces is absolutely nothing. Well, all it adds is a bunch of red herrings that, if you pay attention to them, will confuse you and will end up getting the wrong solution. Implement and interfaces is part of inheritance, but interfaces included in that. Interfaces and your variable types. Ignore them all. Ignore every variable type in your traces. Not in your code. In programming, you have to understand polymorphism. In tracing, you have to understand that you can just ignore polymorphism. Everything to do with polymorphism has to do with typing. And typing, like we mentioned last time, is a compiler check. The compiler cares about typing. When it's a trace, we're talking about runtime. That means the compiler already did its thing, the code's already compiled, and we're running the code. And there is no time in CSE116 where I am going to give you a trace on the midterm or the final exam. I am never, ever, ever going to give you a trace. Never, ever. Well, not this semester. Maybe sometime in the future I'll decide to do this. So don't call me a liar. But I'll never this semester give you a trace where the answer is nothing happens because this doesn't compile. Done. That's not going to be the answer to any of the traces I give you this semester. I'm not going to throw a trick question at you like that. I don't think that's a fair question, and if you put that as your answer, you're guaranteed to be wrong, because I'm not going to give you a trace that does not compile. Certainly not intentionally, as a long time ago happened in the past where I accidentally gave one that didn't compile, but and had to address that situation. But I won't do that to you. I won't give you a trace that doesn't compile. So you can assume everything compiles, meaning all the compiler checks, all the type checks, including all the polymorphism, everything works the way it's supposed to. And then what actually happens when methods are called depends on the object types, not the variable types. So just ignore all the variable types, including interfaces. The interface will not have any effect. The interface is a contract that says if you implement the usable interface, you have to implement this use method. So we have to have a use method in both these classes. We don't have any choice. And if we're doing a trace, you know that the contract for the interface has been satisfied. You don't have to double check that or anything. You just ignore the interface. Interfaces can't have constructors, so it doesn't add another super constructor call. Can't have a constructor, so how are you going to have a super constructor call? So ignore implements usable, ignore the interface, ignore all that stuff. But what the interface says is that we have to have use, and we do have use in both classes that implement the interface. So we create potion and weapon with super constructor calls to game item. That still happens. Pick up weapon, pick up potion. So we're adding them to our inventory. Our inventory is of type usable. Both weapon and health potion are usables. Implements for the is a relationship. Implements works the same way as extends. Potion is a game item. Potion is an object. Potion is a usable. So potion has 4 different types in this example. We added usable to the list. So it can be stored in variables of type usable, and our inventory can be of type usable, the interface. This is why we would use interfaces, is to have variables of the interface type, and we can guarantee that whatever object is stored in that variable has all of the methods defined in the interface. That's the value of interfaces, especially when you already extend a class. You can also add any number of interfaces. So if you want to work with that interface, you can do that. So in the main in this fall and spring semesters when we run the full game engine project, we have interfaces for renderable as sprite and blanking on the other one. Renderable as sprite and no, something else. I forget what. But renderable as sprite. So we have these game objects that extend the game object class. They can be extend static game object or dynamic game. There's a whole bunch of details we don't have to get bogged down in. But we already use our extends for to define that it is a game object. And then we also, if it's able to be rendered to the screen to the user, we also implement the renderable as sprite interface. So the GUI that's displaying everything to the user can work with the renderable as sprite, and it doesn't have to care if it's an actual game object or not, because we can have GUI elements like the like menus and I'm blanking on the, I guess just GUI element. All the overlay, like the overlay, your health bars and I don't know, ammo count, whatever else is displayed to the screen that might not be objects in the game, but are renderable as sprites to the UI. Well, we want those to work independently of game objects. So we have a separate interface for that, and then work with that interface in that system. And yeah, a bunch of those things happen to be game objects, but they don't have to be. And then they also extend game object. So now we have also our physics engine, which our physics engine works with our game objects and just updates all the physics for game objects and moves them around, applies gravity, does all the physics stuff. And as long as we give it game objects, which are broken into dynamic game objects that can move and static game objects that can't move, and as long as we use those classes, it doesn't matter what is happening in the actual game. We can have 100 different types working in a level. The physics engine just works with it all because it just works with game objects. That physics engine is one of the things that would be next to impossible to write without polymorphism, because if you want to, say, detect collisions between objects, you would have to have an array list of, or some data structure, an array list of every single different type of game object you can have in your game. So say you have 10 types of game objects. You have like the player, enemies, 2 different types of projectiles, the goal, walls, floor tiles, I don't know, and a couple other different types of enemies. We'll just add more enemy types. And you'll have to have an array list for all 10 of those, and then you want to detect collisions on a frame. You would have to go through, okay, array list 1, iterate through everything in array list 1, and for each value in array list 1, check everything in array list 2, and array list 3, 4, 5, 6, 7, 8, 9, and 10, and then go to array list 2 and check everything with 2 versus 3, 4, 5, 6, 7, 8, 9, and 10, and do every single combination of pairs of array lists and check the collisions between all of them. That's a pain in the ass. With polymorphism, we have one array list of type game object, and we iterate through all of the elements pairwise and do all the collision checks like that. So polymorphism significantly reduces the complexity of a large complex code base, especially. As your code base gets larger, polymorphism is more and more useful by several orders of magnitude. Okay, tangent over, let's get back to this one. So we picked up our weapon and potion, added it to our inventory, which is of type usable, so we don't care. We can mix types in here, but as long as it implements the usable interface, we can put anything in our inventory. Separate from game items, that's why I went on that tangent. So usable, things can be usable without being game items, and that's fine, because we have a separate interface for usable. So if we want to use like a switch on a wall, well, that'd probably be a game item actually. I don't know, use the save feature. That wouldn't go in your inventory. What's something that would go in your inventory that's not a game item? Maybe the knowledge of a password. That's not really inventory. I'm blanking on an example. And then we're going to call use all items and just use up everything in the inventory. So we're going to equip the weapon and drink the health potion. use up all those items. This isn't a perfect example. They'll still be in our inventory after they're used, and it's got some awkwardness if you think about this in a real game. But a lot of effort was made to try to condense this code as much as possible, so I don't have to scroll too much during the trace. If we try to make it realistic, it'll just be absolutely massive, and it'd take a whole week just to trace it. But let's finally get to that trace. So trace practice. Show me my toolbars. Switch to Java. Destroy everything. Hide the toolbar. Go into full screen. Resize this. I don't think I'm printing anything. Literally nothing. Oh, holy crap, we can fit the whole thing on the screen. Sweet. Yeah, never mind what I was saying earlier. We got everything on the screen. We can even squish this, give us more room for our stack and heap. And let's trace this thing. Who's ready? I'm ready. Let's do it. Okay. New player. Well, first, main stack frame. Player. We're creating a new player. We have the constructor. We have the object, which is type player. Player. This. We got OX100. And this is just regular object creation for this one. I guess the new thing is the default constructor. But we're not even using inheritance anymore. I don't see extends here, so I'm just ready to start rolling. We have 3 variables outside all the methods, so we have 3 instance variables. Capital HP, damage, which in this case is the amount of damage that a player will deal when it attacks. Again, code is stripped down for the example. In the repo, we do have larger versions of these classes, but again, trimmed down for lecture. And these are all instantiated or assigned in line. And then we have new array list. So we do have the keyword new being hit again. We have array list. It's been a while since we've seen an array list. And it currently doesn't have anything in it, so I'm going to delete that. And we got OX200 as inventory. I don't see any constructor, so I get the default constructor. Still has the keyword this, but it has no parameters. This is, I keep mentioning this, but this is a common mistake I always see. Just because we have 3 instance variables does not mean those instance variables go in the stack frame. The constructor is a method call. It follows the same rules as method calls. It doesn't get extra stuff just because it's initializing an object. It doesn't get copies of the instance variables directly. We have a lot of examples where the constructor is used to initialize all the instance variables, and that just happens to be the case. But here's a situation where that absolutely is not the case. If there's HP, damage, and inventory in your constructor stack frame, that is absolutely wrong for this code that we're tracing now. That's just stuff that students like to just make up. I think it's because they overstudy certain traces from lecture where that is the case just by happenstance, without actually learning how to trace through code. If I see that stuff, I know you don't know how to trace through code. That's something you got to study more and get right on the final exam. You got to get those. Got to get that. So constructors, just like any other method call, it's a non-static method call. So we have the keyword this. Other than that, it's parameters. The parameters go here. There are no parameters. We get the default constructor. Nothing to do. And this just returns OX100 to the main stack frame. So a regular object creation without inheritance. That's how easy things used to be. And then new weapon. So let's get our weapon. I always forget my arrows. I'm going to put it right away so I don't forget it this time. Weapon. New weapon. Map the constructor. This. We got OX300 this time. We have 2 parameters. Not looking at the constructor yet. Let's just get the parameters here. -5.0, and 15. And then we're looking in the weapon class. Weapon has instance variables damage. And nothing else in the weapon class, but we do extend game item. For our traces, we ignore interfaces. They don't have instance variables. They don't have constructors. They literally can't affect our trace. There's nothing I can put in the interface. It's actually going to affect the trace. But we do extend game item. Extend still has the same meaning as it has before. So we have the game item constructor. We're still doing instance variables. We have the game item, which has an instance variable location. And I turned this into a 1D game, by the way, just because, again, less space for the trace. So we have those two instance variables. Then we're ready to run the weapon constructor, which has parameters location and damage. And then we're ready to call the constructor, which immediately we get a super constructor call. The super class is game item, so I know I'm going to have a stack frame for game item. This is still the same reference, OX300, to the object that's being created. And then we have one parameter location, which gets location from the weapon constructor. So the weapon constructor location was -5. And then what the code actually does is initialize location. So this dot location equals location -5. This constructor is done, and we're going back to the weapon constructor, which initializes damage. This dot damage equals damage. So damage gets 15. This returns and gives OX300 back to the main stack frame. So this is an object being created that had a super constructor call. So weapon extends game item. If you're creating a weapon, you better have your game item constructor there, because game item constructor is responsible for initializing location. That's the only way that instance variable gets initialized in this code, is through that super constructor. Very important that you know it's being called. If you're writing code in your future and you don't understand super constructors being called, you might be wondering where extra instance variables are coming from, how they got initialized, what happened there. It's because you called the super constructor. It always is called, whether it's explicit or not, and that super constructor is doing some work for you to help initialize that object. Then we have potion. Which I shortened to potion, again, just for space. It gets tedious typing health potion every time. So it's just a generic potion now. Potion, this, we got OX400. We have one argument, 3.5. And we're looking for the potion class. So potion has no instance variables, but does extend game item, which has a location instance variable. So we just got one instance variable here. The potion constructor takes a parameter named location. And all it does is calls the super constructor. So we have game item, which is what potion extends. This is still a reference to the object that's being created. And we have one parameter location, which gets the value location from the potion constructor, 3.5. And then this dot location equals location. So this dot location equals location, 3.5. Super constructor returns back to the potion constructor. That's all it does is call the super constructor. So this is done and returns OX400 back to the main stack frame. So all those so far were review, aside from the first time we're tracing a default constructor call. Actually, the next thing's review too. We've done these. These use all items that we're building up to. Player.pickup weapon. So player.pickup. So we're calling pickup from OX100. right here. So we're calling pickup from OX100. So this is OX100, a reference to the object that's calling the method. And we have one parameter. I have the argument here first. Weapon is OX300. So we're giving OX300 to this pickup stack frame. And it's player. We're looking for a method named pickup. It takes one parameter named item. That parameter happens to be of type usable. For my trace, I don't care. I don't even have to look at that because I know the code compiles. If this type didn't work, if weapon wasn't usable, then this code wouldn't compile and it'd just be a broken question. But we do know weapon is a usable. Here it implements the usable interface. So we know that's a valid assignment. But for a trace, I'm always going to give you valid assignments. So we stored a weapon in a variable of type usable, perfectly legal assignment due to polymorphism. And we're going to add that to the inventory, this.inventory.add. So this.inventory.add, we're calling add from this array list right here. So we're adding something into index 0, and what we're adding is item from the pickup stack frame. Item is OX300. So we added that item to the array list, then the pickup method ends, and we're ready to just run it back, call pickup again. So player.pickup, pickup, this is OX100 again. And this time we're picking up potion. Potion is OX400. So OX400, and our argument is still item. And we can check our types again. Potion is of type usable. The object is of type potion. That's why it's important we put our object types on the heap, because we need to know what the object types are to know what behavior these things are going to have. But this potion is stored in a variable of type usable, so we can only use this potion in cases where we can use usable. And we're going to pick up the potion. So we have pickup, which is usable. So we have usable item equals potion, which is of type usable. Usable is a usable, so that's fine. Potion is a usable, so this assignment's fine. So all our assignments work out, and we're able to store OX400 in item because OX400 came from a variable type usable. The types match, and that's fine. If pickup took a potion, that would not be a valid assignment, even though this variable does refer to a potion. The object type matches out. The variable type doesn't. You can't take a usable variable and then assign it to a potion variable. It's not gonna work out, even though it happens to be a potion in this case. But here we got away with it because we have usable assigned to a usable variable. Everything's fine. Everything's fine with that. So we have this dot inventory dot add. So we're adding something to the next available index, which is 1. And what we're adding is item OX400. This method call returns. Back to the main stack frame. If you ever lose track of which method is executing, you start at the bottom of your stack and go down until you find a method that's not crossed out. That's your currently executing stack frame. So that's the main method right now. When you have like 5 or 6 method calls on the stack, can get a little easy to lose track of what's going on with them. But it's the lowest one that's not crossed out. That's the active stack frame. The crossed out ones don't exist in memory anymore. And the stack is a stack data structure. It's this last in, first out data structure. So whatever's on top of the stack, which is the bottom visually, the way we do our traces, whatever's on top of the stack is active. And whenever it's removed, it's the next one underneath it that's active again. So player.useAllItems. Player.useAllItems, so use all items from player, which is OX100. And we're looking in the player class for use all items. and we are going to use all the items. We have a loop where it's a for loop, so the initialization, the variable here, is created inside the stack, the code block for the loop. So we do need our code block in this case. We have item, which is iterating over this dot inventory in a for each loop. So this dot inventory. So we're iterating over OX200, which is this array list. So we're starting at the first element, OX300, and then we'll go on to 400. So item is OX300, and then it's item.use of this. This is a line that can be a pretty trippy line if you're just reading the code. I think it's a lot easier in a trace because, again, with traces, I like to turn my brain off a little bit and just blindly do what the code's telling me to do. I have item. Item is OX300. I have the dot operator, which tells me I have a reference, take me to your object. So I hop over to the heap to this weapon object. And I'm going to call the use method. So I know I have a method call of use in the context. This is OX300. And I have one argument, which is the keyword this. So I have another variable. I don't know what the parameter is yet. I haven't looked yet. But I know the argument is this from the use all items stack frame. So if I go to the use all items stack frame and look at what this is, well, it's OX100, OX100. I don't really have to think about keywords or whatever everything means. This in the use all items stack frame is OX100. That's what my parameter is. So my parameter is going to get. So now the big question of which method is going to be assigned. Remember, for these OOP, for the inheritance part of OOP traces at least, it's don't forget your super constructor calls. Seriously, don't forget your super constructor calls. I say so many times, there's no, we go through quite a few examples, there's no way to miss those. Plus, if I make them explicit, you have to just ignore the actual super constructor call line, which does kind of baffle me. I guess it makes sense. If you're learning this for the first time, maybe you just, you can't internalize everything in a short period of time, especially in the summer. But there was some miscommunication between us at that point if you're missing super constructor calls. Maybe I got to say it twice as many times. So I have the use method called from OX300, which is of type weapon. We always look at the object type. I emphasized this last time, but the object type always matched the variable type before. Here, the variable type is item, which is usable. The variable type is usable. If we go to the usable interface, we don't really find anything interesting. We find the use method. That has to exist because we're calling the use method. So whatever the variable type is does have to know about this method, this method's existence, but it doesn't have to know what it does. In this case, it doesn't. It's abstract. It doesn't know what it does. So that's not going to get us anywhere anyway in this case. We have to look at the object type. The object type is weapon, so we look in the weapon class for a use method. We find it right here. This is the method that's going to be called. We can find our parameter now is called player. And it's player.setDamage. So player.setDamage from this object right here, OX100, we're calling setDamage. This OX100 takes one parameter, which is this dot damage from the use method. So use this dot damage is 15. And then set damage from OX100, which is of type player. We look in the player class for a set damage method. We find it right here. And as we could kind of guess in this case, it's just a setter. Has no data sanitation. It's just a straight up setter this time. So this dot damage equals damage. We just increased our damage output from 4 to 15. And again, yeah, 4's crossed out don't look like they're crossed out. We gotta fix that at some point. So this returns. We go back to the use method from the weapon class. So we were in weapons, use, it only has one line, so we're done with that. Cross that out. Both these methods return void, so nothing to return. And we're back in use all items. Use all items was at this line right here. So that did its thing. We hit the closing brace of the loop. So we're on the next iteration. We're at OX300. We're moving to the next value, OX400. And going through the loop again. So we're doing item.use again. So we have a use method call. We have item.use, so we're calling it from OX400. And that object is of type potion. Again, the object, not the variable type. It's always the object type. The object of type potion, we're going to look for a method called use, and we do not find it. The potion class doesn't really have anything here. We do not find a method named use, so we look in the super class. Again, ignore those interfaces, ignore implements and any interfaces in your traces. It still always extends, just like we did last time. So extends game item. Game item is the super class. There's no like super interface. It's always a super class. Look in the super class for a method named use, and we do find it right here. We find it right here, and this is the method that's going to be called. So we go through our progressions just like we did last time. We find the method in the superclass. Now some interesting things happen here. Let's actually get a little more values on the stack here first. But player is the parameter. The argument was this from use all items. So in use all items, this was OX100. And we're doing player.setHP, player.getHP plus 20. Before we do all that, let me just emphasize, kind of highlight what just happened here. So Potion implements the usable interface. Just the way we go through everything works out fine here, but it seems weird on the surface because Potion implements the usable interface, which says, Potion, you must implement a method named use that takes a player and returns void. Has to happen. You have to implement this method. And Potion was just like, nah, I don't want to do anything. I'm just going to forward my constructor call to the super constructor call, and I'm not going to add anything. I'm basically just a game item. Potion adds nothing of its own. But this code compiles. It still satisfied the contract for the interface, which is kind of weird, kind of strange. But it got there by extending game item, because game item did implement the use method that takes a player and returns void. It gave a definition for that method, yet the game item class doesn't implement the usable interface. Game item had no obligation to implement this method at all. It just did it out of its own free will. It just happened to implement that method. And when Potion extends game item, that alone still gave Potion a definition for use that still satisfied the contract. So just by extending game item, that alone satisfies the usable contract because game item already happened to have a method. It didn't override this method. There's no override annotation, but it did still satisfy the Potion's contract that it had with usable. Now the way we go through our progressions, this is kind of automatic. We have a method call from a Potion object called use. We don't find it here. We go through our progressions. We find it here. Therefore, Potion did have a definition of use. That's fine. So through Potion, we can call a method named use that takes a player. Therefore, it satisfied its contract. So as long as it has a method, it doesn't matter if it got it through inheritance or defined it on its own. As long as it does have a method that satisfies the interface, it's perfectly fine. So a lot of nuance there, a lot going on there. I would say you don't have to understand all the intricacies of what I just said for 116, but it is an interesting use case of inheritance, polymorphism, and interfaces. Okay, so now we have this use method. We always do resolve what's inside the parentheses first, just like in math class. Usually I still work from left to right, but this time we have to think about that a little bit more because we have this method call which is going to need to be resolved before the setHP method call goes on the stack. So let's get this getHP on the stack. This, we have player.getHP from the use method. Use player.getHP, so that's being called through OX100. So this is OX100, the object that called the method, which was player, whatever stored in the player variable. That's the object calling getHP. Player variable has OX100. So getHP from OX100, that's of type player. Player getHP is, oh, without my this dot, I'm adding my this dot. Return this dot HP. So this dot HP is 50. This will return 50, not into a variable, so I don't have any return arrow, but I have 50 plus 20, so we're going to have 70. We're going to call set HP from player. So this is player, which is OX100. And we're going to set the HP to 70. Player set HP, the parameter is HP. Nice consistency. And what it does is this dot HP equals HP. This dot HP equals HP, which is 70. Method returns, doesn't return anything, returns void. We go back to the use method. We just did all of that. So we're done with the use method. We're back in use all items. Use all items was waiting for this method call to return, so we pick up right there. We're at the end of our loop. We already iterated through both values in our data structure, so the loop's done. Cross out the code block for the loop. Then the method's done. Cross out the code block for the method. Brings us all the way back. All these are crossed out. We're all the way back to the main method, which was calling use all items, and that's the end of the main method. Cross out the main method too. End of trace. So quite a bit going on with this trace. Actually, I mean, it is quite a bit, but I'd say this is about the complexity of an OOP trace. Yeah, it's about the complexity of an OOP trace. There's one thing I would add to it, but I would also remove the player object. The player object is isn't necessary to really assess everything that I need. But there's assignment by reference is missing. I would have like player 2 equals player in this trace. But this is roughly the complexity of a trace that you'll see on the midterm and final exam. Well, anybody listen to me, especially if you're listening to me live, you're probably not going to the final. You're going to crush this on the midterm. And it's also the complexity of the sample, the OP1 and OP2 that I posted today on Piazza for the sample questions, the practice questions, is about the same complexity. So if you can follow this, you're probably doing pretty good for the exam, especially if you can follow this to the point where you can recreate this. And you are ready. You have everything you need for OP1 and OP2 practice questions that are on Piazza. So you can start practicing those right now. They'll feel roughly the same as this. They don't have interfaces. Especially when I say interfaces, you just ignore them on your traces. Is there really a point to putting them on the traces? I still want to show it in a lecture example at least, but really do I need to put them on there just so you know to ignore it? It's kind of just a waste of space on the trace in question. And if there's any confusion on this, I mean, as always, give me your questions. Post your questions in chat. This will be here for a little bit. We will start some slides up again. And then we do have another memory diagram today. We do have another memory diagram today, so I do have to wipe it eventually. But get your questions in there if you have any before then. The big things are the superconstructor calls, the which method is being called, going through our progressions. When we called use from weapon, we found use right here, called it. We've called use from a potion, don't find it, continue our progression to the superclass. We do find it here, and then call that. None of that changed when we have inheritance. So even though both of those objects were stored in a variable of type usable, that didn't matter at all. The variable types do not matter. Just ignore your variable types when you're doing a trace. The object types are the only thing that matter during a trace. Variable types, of course, matter when you're writing code, but when you're tracing code that's already written and is guaranteed to already have compiled, the object types are the only thing that matter. That's why those are the only types we actually put in our traces. We have never put a variable type in any trace. It's only the object types. From 115 and 116, that's always been the case, and for a very good reason. It's all pretty much building up to polymorphism, where the variable type and object types are different finally. That's where we don't want you getting confused by the variable types. Some students will like to really overanalyze the code on a trace. Don't do that for a midterm question. Don't overanalyze the code itself. If you're looking at the code too much, you're inevitably going to get the trace wrong. You should be looking at your trace to find the next step. I'm constantly looking at the trace. I'll look at the code just to see what the next line is telling me to do, but then I immediately get all my information from the trace. If you watch carefully how I do the traces, I'm getting all the information from memory. I'm not looking back at the code. Once I'm done with a line, I will never look back at it. That line of code is done. All of its effects are already living in memory. I never have to look at that line of code again. I suppose unless it's in a loop. Then I gotta go back to it. But only just through the natural code flow, control flow of the program. I'll never backtrack through the code. I believe students do that a lot. Maybe they're just shaky on traces still when they do that. But don't do that intentionally. Only do that if you're really stuck and just don't know how to do tracing. If you didn't study enough, then yeah, maybe you can do that out of desperation. But the real answer is just study enough. Practice these traces. We got the practice traces on Piazza now. You got study material. Take advantage of it. Okay, comparators. Let's do some sorting. And we're only 2 minutes ahead. This one is a pretty big lecture. Hopefully we can still finish this one. This is one that moved. I think this is the biggest reason why last lecture went by a little quicker than I expected, because we moved this content to the end of polymorphism. It used to live at the end of inheritance. I think it threw my timing off. But we got a lot to talk about with this one. Let's talk about sorting. Oh, I gotta just reset my brain for a second. I'm thinking about polymorphism still. All right, so let's talk about sorting. Let's shift gears here. So let's talk about sorting. This is where we will use that comparator interface. I set it up in the last lecture, and we talked about it again in this lecture. Here's where we're really going to actually use that comparator. The way we're going to see it introduced today is going to be as a class. Actually, I think in the trace it might still be a class. I don't forget if we updated that or not. Actually, let me check real quick. Just suppose we could always change it if it's not. Yeah, it's still a class. I'll leave it as a class. It'll let me talk about the difference between interfaces and classes and why it makes more sense as an interface than a class. So what we want to do, what I want, is to be able to sort data structures. That's our ultimate goal today. To do that, we're going to use comparators. So comparators are going to allow us to compare exactly two values of the same type. And polymorphism can apply here. It won't in our example. We'll just use integers. But it's going to compare two values of the same type. That's it. And we're going to use these comparators to sort any arbitrary number of values in a data structure. So let's learn about comparators first. And then we'll talk about how we can use comparators that can only compare two things and use them to compare any number of things. So there are two styles of comparators, two main flavors of comparators that we'll see. The one will take, they'll both take two values that we're comparing. One will return an int, one will return a boolean. The one that returns an int, this is the one that Java's built-in comparators use. So whenever you're using Java built-in methods, they're compared to methods, that style is going to return an int. And specifically when we want to compare two strings and sort strings alphabetically, these are very handy, especially if we want to ignore capitalization in our strings. That's where this comparator really comes in handy. So we do kind of have to use Java's built-in comparators sometimes, and that style is ints. When we write our own comparators, we're going to write one that returns a boolean. So two different flavors of comparators. Let's talk about them. The one that returns an int follows a very strict structure, and in Java, these comparators are methods. They're non-static methods, so they're called through an object. So we have two references being compared with the compared to. One is the object calling the method, which will be in the keyword this in the compared to method. I'll commonly refer to this as the first one. And then the second one will be given as an argument, and it'll be stored in a parameter in the compared to method. Those are the two objects being compared. So if the first one comes before the second one, the compared to method will return a negative integer. If the two values, if the parameter comes before the calling object, or the second one comes before the first one in fully sorted order, it'll return a positive integer. And if their relative ordering is the same, it'll return 0. So here A comes before B, so we get a negative value. A comes at the same time as A, so it returns 0. And B comes after A, or A comes before B still, so it returns a positive integer. Now a lot of these compared to methods will return exactly -1, 0, and 1, but do not fall into the trap. This is a trap every programmer falls into at least once, myself included, where you'll write code that says, if compared to equal -1, do this, else if it equals 1, do this, else it must be 0, so do something else. It's not guaranteed that all compared to methods will return -1, 1, and 0, even though a lot of them do just by convention. It's just the way they're coded. When you write compared to methods, sometimes you'll write them to do the same thing. And that's fine, but when you're using a compared to method, it is a negative value, a negative integer, a positive integer, and 0. So your conditionals need to be if compared to is greater than 0, less than 0, or equal to 0. Those are your three comparisons. Those are the three checks that you want to do. Don't fall into the trap of getting a compared to result of -20 and having that be treated, have some bug where that's not treated how you want it. In the example I gave, it would be treated as equivalency in the sorting order. You don't want that. So this is the style of comparator you'll see in Java. If you ever need to use one of these, that's what the protocol is. That's the expectation that it's what it's going to return. For strings, the compared to method is going to sort strings alphabetically for the most part. The problem with this is it does treat capital letters differently than lowercase letters. So, and specifically, it'll sort strings by the character codes of their characters. And I won't read all the bullet points here, but it's kind of what you would expect. If a string's a substring of another string, the substring comes first, etc. And it'll go character for character through the strings. And then the first time it has a mismatched character, then whatever character comes first, that string comes first. The problem is that all of the lowercase letters come after all the uppercase letters. Specifically in ASCII and a lot of other UTF-8 and other character code encodings, the lowercase letters come after the uppercase letters. So if you have a word that starts with a capital Z, that's going to come before a word that starts with a capital A, which is probably not the ordering that you want. You probably want actual alphabetical ordering that ignores case. And Java does give us, in the string class, gives a method named compared to ignore case. So if you do want to check sort strings while ignoring case, there are methods for that. Compare to ignore case equals ignore case. Remember, if you're comparing two strings for equality, make sure you use the equals method. Do not use equal equal to compare two strings. We will finally explain why that is the case when we get to next Tuesday's lecture. I briefly explained it in a previous lecture, but just to reiterate, equal equal on strings, on any references, we'll check if the references are equal. Strings are actually objects. We pretend they're values, but they are references to objects on the heap. So if you have two strings that are identical, two string variables that store the identical strings, but they're different objects on the heap, if you use equal equal, that's going to be false. But if you use dot equals will go character for character and check if those strings have all the characters the same, which is probably what you want if you're comparing two strings. You probably don't care if they're in the same object on the heap. You care if they have the same characters. That's the important part. So always use equals, the equals method, to compare two strings for equality in Java. It's different in other languages. In Java, that's what we got to do. And that does come up. I think it's in your linked list, right? You got to delete a string from a linked list. You have to know if it's equal to the string you're trying to delete. If you're using equal equal there, you're just asking for trouble. You got to use the equals method to compare two strings. I think that's the first time it comes up. Okay, so that's Java's built-in comparators. The comparator that we'll focus on in lecture, that we'll talk about the rest of the time, the comparator that we'll write. Oh, man, I forgot I'm still in the middle here. I don't think that mattered, right? So the style comparator that we'll work with returns a Boolean. What this will return is true if, and this will be a method that just takes two references. There won't be a calling reference and a parameter reference. They'll both be parameters. So if the first parameter comes before the second one, return true. Otherwise, return false. So a much simpler description, much simpler setup. If the first parameter comes before the second one in fully sorted order, meaning if you had these two values in a fully sorted array list, and the first one has to come before the second one in that fully sorted list, then return true. Otherwise, return false, including ties. So if the second parameter comes first or their relative order does not matter, return false. So this is the style we're going to be working with. So let's start diving into this style of comparator that returns a Boolean. So the default comparator is the less than operator. We're going to use greater than here, but the default one is the less than operator. If we use the less than operator, we're going to get our values, ints in this case, sorted in increasing order, which is the standard sorted order that you would expect if you're sorting integers, that you learn in kindergarten. If you're sorting numbers, 1, 2, 3, 4, 5, 6, 7, it's the regular sorted order. The less than operator is going to get you that. So if I have 10 and 15 that I give to my comparator and I'm using the less than operator, it's going to return true. Yes, 10 does come before 15. That's the less than operator. We're going to check, is 10 less than 15? If 10 is less than 15, it comes before it. If we're writing custom comparators, we got to do at least something that's not the default ordering. So I did the simplest thing that's not default ordering. We're just going to sort our integers in decreasing order. For that, we're going to use greater than instead of less than. So now 10 and 15 is going to be false, because 10 does not come before 15 if we're starting with the largest values and going down, going in technically non-increasing order. But if we're going in, but I'll say decreasing. Yes, I'm wrong there, but it's too many syllables to say non-increasing every time. And we'll get that decreasing order for our fully sorted order. So the greater than operator will give us that. And if I say 10 and 10, it's going to return false. So ties are always returning false for our comparator. So we're satisfying the structure of our comparator. And when we create, we want this method in a class. Like, this isn't legal Java code. We need this in a class. So we're going to create a class. I'm just going to call it int decreasing. It's a comparator that will sort our ints in decreasing order using the greater than operator. It'll have one method to compare two values. It returns a Boolean and is the greater than operator. And that's it. And here's where finally the default constructor comes up officially in the slides. There's no constructor for this, but we have a non-static method. So we need an object of this type to be able to call the compare method, because it's non-static. That's what we need. There's no constructor, so how are we going to do that? Well, never fear, we have the default constructor. So if you don't write a constructor, that's equivalent to getting the default constructor, which is public, takes no parameters, and has an empty body. So these two classes are identical. They do the same exact thing. We would get the default constructor for free without having to write it. This is the third time it came up in the class, so I don't think I have to dwell on this too much. But here it is visually, is we get the default constructor for free without having to type it. But we also want, well, I just want to use inheritance, right? Okay, is that so bad? Is that such a bad thing? So we also want an actual comparator class. There is a reason for setting this up with inheritance, and the answer is polymorphism. We'll get there when we start sorting. But let's set it up for now. We want a comparator, but we want to be able to compare any type with our comparator. So our comparator class is actually going to take a type parameter, because our ultimate goal is to be able to sort any type in any way and write a sorting method one single time. That's our ultimate goal that we're building up towards. We want complete flexibility. And one way that we know how to get flexibility that we saw with linked list is to take a type parameter. So I want to be able to compare anything. So I'm going to have a comparator of a type parameter and say, if you extend me, you have to have a compare method that takes two values of the type parameter and returns a Boolean. Now, if we're not embracing abstract methods, like this can be an abstract method and this can be an interface instead of a class. If we're not embracing this, we have to give some default behavior to our compare method if we don't use abstract at all. We have to give some default behavior. So only two default behaviors we can really choose here is return true or return false. Actually, now that I look at it, I suppose we could do a dot equals b, and most times it'll compare references, or just a equals equal b and always compare references. I suppose we could do that too. There are other options, but anyway, there's no meaningful default option here that would be helpful. But we have to give one. If we're not using an abstract method, we have to give some default behavior, and then when we override the method, so we're going to extend comparator and override the compare with something actually useful. If we mess up our override, if we don't have our annotation and have a typo, then we're always going to get the default behavior by accident, and nothing's going to warn us about that. So this is a perfect spot for an abstract method. And in fact, it's a perfect spot for an interface. If you don't need instance variables or constructors or concrete methods, make it an interface. If you can make it an interface, make it an interface, because it gives you more options to do multiple inheritance with multiple interfaces, and also extend another class. Don't use the class extension if you don't have to, because you only get one. Here I am using it up, but if we have this as an interface and compare as an abstract method, now we have to implement it And it doesn't matter if we don't have our override and we don't have any other protections in place. If we have any mistake where we're not actually overriding compare, since it's abstract, we'll get the compiler flagging us down and saying, hey, you didn't satisfy your abstract method contract. You have to implement that method. So it's another safety net in place, especially when there is no meaningful default behavior. We don't want anybody actually using this return false. Nobody should ever actually use that. So if we have it as abstract, that's us saying, I want this method to be known to comparator. So if I have a variable type comparator, I know I can call compare because it will exist, but I have no default implementation to give you. I'm leaving it up to my extending classes or implementing classes, if it's an interface, to define what compare actually does. So this is a prime candidate for being an interface with one abstract method. I will leave it as a class here just so we can see what the other side looks like if we don't embrace interfaces and abstract methods. And then we can't have compare of int like we had before. We do have to change this to integer since we have a type parameter. This has to match the type parameter, and this is an easy mistake to make, and by that I mean I made this mistake, is if compare takes two ints. Usually Java's good about autoboxing, but in this case, since integer is a type parameter and I have to have a method that takes two objects of the type parameter type, if I take two ints are not integers, and I did not override compare. So if I don't have my override annotation and I have int and I'm not using abstract methods, well, now when I create a class of type int decreasing and I'm using that to sort, my compare method always returns false. Everything kind of on the surface seems right, but I had a multitude of opportunities to be able to catch that mistake, and if you miss them all, you can have a mistake there. Int does not equal integer. Don't use your override annotation, and don't use abstract methods if you just say, you know what, I know I learned all that stuff, but I don't want to use any of it. You might have some bugs like that in your future. So just be careful, use all the tools available to you, and avoid bugs like that. Nothing to add for that slide. That slide's, if you don't know abstract methods yet, you have to give some default behavior. So we have the stubbed out compare method that just returns false. But we already know about abstract, so we would just make it abstract. And your comparators can get very complex. So we are using full classes here. We have a class that extends comparator of game item in this case. That means we have a contract to write a compare method that takes two game items and returns a Boolean. But we can add more than just that. It's not like we're restricted to only adding that compare method like we had in the int decreasing method. And we will switch back to the int decreasing method just because that one's much simpler. I want to have a simple example that we're working with here. But I also want to emphasize that your comparators can be very complex because we have a full class that we're creating. We can do anything that classes can do. We can have instance variables and constructors and helper methods. We can do whatever we want here. So if we want to compare our objects in very complex ways, well, we just write the code to do that. That's perfectly fine. As long as compare takes two game items, that's fine. So here, if I want to sort game items based on their distance to the origin, and here I'm using less than, so the first value in my fully sorted list will be the item closest to the origin. I can do that by I'm going to write a helper method just to keep my code clean so I don't have to copy and paste this twice in my compare method. And I'm going to compute the distance to the origin and then compare those two game items based on their distance to the origin. Whatever's closest to the origin is going to be earlier in the list. So if game item A is closer to the origin than game item B, then it'll have less distance. This will be true, which is how we denote that the first parameter should come before the second parameter. And we can take this a step further. Like distance to the origin, maybe not that useful in our game, but distance to the player will be. So we could expand this a little more if I have a constructor. Let me back up a little bit. So if we want to compare distance to the player, what we kind of want is the compare method to take a third parameter, which is the player object. But we're not allowed to do that because compare, our contract with the comparator class, compare has to only take two values of the type parameter type. That's all we're allowed to work with in the compare method for parameters. But if we want more context and more information, well, we're calling this from a class, and it's a non-static method. That means we're going to have the keyword this in here too. That means we have access to any instance variables that we might define in this class. So if we have instance variables in a constructor to initialize those instance variables, we can use any of those instance variables in our compare method to help our comparison. So we could add a constructor that takes a reference to a player, store it in an instance variable, then update our distance method to subtract the player's x and the player's y, and then get the distance to the player from this distance method, and then we're sorting all of our game objects in terms of distance to the player. So anything you can think of, I want to sort by whatever, we can write a comparator that's going to do that. We can add enough, whatever code we want to this class to be able to get the job done. And in fact, in that example where we're sorting by distance to the player, well, the player is going to be moving around constantly, which is actually fine because we didn't take the player's location, we took a reference to the player. That means when we use this comparator again after the player moved, we're going to get this.player.getx, this.player.gety. Well, we're actually going to the heap and getting the player's current location because we have the player by reference. That reference is going to be updating, and even as the player is moving, our comparator is still giving the right answer. We might have to call our sort method every single frame to get the player's latest location and resort everything. That's usually a cost we're willing to pay, especially when there's, less than 100 game items maybe in our game. Even if there's thousands, sorting every game frame 60 times per second, it's still pretty small numbers for a computer. We can do that. We'll usually do that to gain efficiency elsewhere, so we don't have really expensive methods somewhere else in our code. Can actually be faster to sort every single frame than working with unsorted lists. So comparing can get very complex. We can do a lot here. We'll go back to our int decreasing example and just sort integers in decreasing order because I want to pull it back and focus on the concept of the day, sorting with comparators and polymorphism and inheritance, and not get bogged down in like the distance equation, computing Euclidean distance. I don't want to get bogged down in that. Plus tracing this, I got to put get x and get y on the stack every single time we get here, and 2 extra stack frames for every compare. It's just more to trace as well. But this is something that we might do in the real world. We're using this as a lecture example, so we have a simpler example to get the concept out there. But the big problem here is that we're only comparing 2 values. I want to sort lists. I want to sort an array list of 1,000,000 values. How am I going to do that when all I can do is compare 2? The short answer is, well, we're just going to call that comparator a whole bunch of times. Problem solved. And this is where our sorting algorithms come in. So I'm going to go through insertion sort, just one of our pretty slow sorting algorithms. In CSE150, you'll see more efficient sorting algorithms. You'll see merge sort for one. But let's just see a slow one, a nice slow, simple sorting method. You might have even seen this in 115, but I want to focus on the comparator side of things when we go through this now. So we have this list that we want to sort, this 167. With insertion sort, what we're going to do is iterate through each value in the input and figure out where it should go in the output. So for the first value 1, there's no options. It's just going to go in index 0. We can't put it anywhere else. That's easy to solve. For 6, we actually have to make some decision. For 6, what we're going to do is go through every value in the output, and for each element, each subsequent element, we're going to go through every value in the output, and we're going to count how many values come before 6. And for that, we're going to use our comparator. We're going to say, for 6, we're going to say, does 1 come before 6? And the answer is going to be no. The comparator is going to say false. Remember, we're using the greater than operator, so we want to sort these in decreasing order. Our final output should be 6, 5, 1 if we do things right. So we're going to say, does 1 come before 6? The answer is no. So the number of elements that come before 6 is 0. So we're going to insert 6 at index 0. And if we follow this for every single value in the input, we're going to get our fully sorted order. By using our comparator and only comparing 2 values at a time, we can still get our fully sorted order. So for 5, we're going to ask this question twice. We're going to go through everything in the output and say, does 6 come before 5? The answer is yes, because 6 is greater than 5. Does 1 come before 5? No. So we don't count that one. So we counted 1 value that comes before 5 in the final output. That means 5 should be inserted at index 1. And then everything else should be moved down. We're going to insert 5 right in between 6 and 1. 1's going to move down to index 2. And now we've gotten to the end of the input, so we're done. And that's our sorting algorithm. For every value in the input, count the number of values in the output that come before it and insert it at that index. That's our whole insertion sort algorithm. In the code, it looks like this. So we have a bit of setup here. We will trace through this one, so I'll go through all the setup in great detail. But we have our input list 165 that we had from the example, the visual example. When we sort, we're going to have a reference to a comparator. We're going to, actually I do want to break this down a bit. We have a reference to our comparator, so we know how to call, how to compare 2 values. It's the only thing we know is how to compare 2 values, but we don't know what the comparator does. We have a comparator of t. We don't even know what t is, and we don't know what the comparator does. And that's the way we like it. That's the way we want it. Because when we write a sorting algorithm, when I write this sorting method, I want to write it one single time ever. And this sorting algorithm works with any type because it takes a type parameter. But I don't know how to compare types. I have toString and equals. I don't really have any way to compare 2 values unless I pull in some more information. So I'm going to also take a comparator. I still don't know what t is. But if you say, hey, I want to sort an array list of something, I'm going to say, okay, provide to me a comparator of somethings. I don't care what something is, but as long as your comparator matches what you're trying to sort, I'm going to use that comparator, which I know must have a method named compare of t and t, because or else it just has to, because comparator knows about that method. So that method has to exist. Even if it's abstract, it has to be implemented at some point. So it has to exist. So I can call this method through a comparator of type comparator of t and give it 2 t's and compare them. I don't know what comparator is doing, and I don't know what t is, but this code will work. Then when I want to use this code, I'm going to create an array list of t, in this case integers, grab a comparator of t, in this case int decreasing, which, I'm getting ahead of my slides here. I think this is all review. I'll leave it on screen for a second, but it's being careful with your references. Then when I want to compare my values, I'm just going to use comparator. Yeah, I got ahead of my slides here. Sorry, guys. And when we provide the int decreasing extends, and this slide was written before we reordered some of the content. So it's going to be like, what's polymorphism? This is allowed because of polymorphism. But int decreasing, we know in polymorphism here, so we can talk about it. Int decreasing extends comparator of integer, And that's what we need. If we're specifying the type parameter to be integer here, we're saying sorter, hey, I want a sorter where t is integer. I have to provide its constructor a comparator of integers. Int decreasing extends comparator of integer, so int decreasing is a comparator of integers. So that's a valid assignment. Comparator of t, comparator equals new int decreasing. That's a valid assignment because int decreasing is a comparator of t, where t is currently integer. It is a comparator of integers, so that assignment is legal and valid. And then when I want to sort, I give it an array list of integers. Doesn't matter what integers I give it. I give it an array list of integer. That matches the type parameter t in this case. So I have a comparator of integers, an array list of integers, and this sort method, which I never told anything about integers, and I never told anything about int decreasing, how to sort integers or anything. This code still works. So I have completely generic code. Works with any type and any comparator, any method that anybody wrote, or some complex class. I mean, I could be sorting game items by distance to a player. This code doesn't know about game items, players, or distance equations. It doesn't know about any of that stuff, and it's fine. Java has a built-in sorting method, and they follow the same principles. It takes a type parameter and a comparator. It takes the style of comparator that returns an int, because that's Java style. But it's the same concept here, is they write one sorting method one time, and it can work with types that you write that didn't even exist at the time when they wrote the sorting method. They wrote one sorting method one time, and it works with any type, with any comparator. And you provide the type, you provide the comparator, that code still works because it's abstracted through that comparator's compare to method, compare to internal to Java, compare in our code here. It works by taking a type parameter and a comparator of that type. You did the same thing in Python in 1.15, except it was kind of simplified. You just said key equals and then whatever you want to sort by. It's the same concept, though, happening under the hood. Python has a sort method that they wrote once. You give it any type and any key, and it'll sort that type on that key. Okay, and let's... where'd those slides go? Just completely disappeared. I feel lost. I just want to make sure. I don't think so, but yeah. Just make sure I don't have anything after those slides. Let's grab this trace code. So this trace code is actually in the inheritance topic, but this is today's trace. Show toolbar, destroy. No, don't do that. Paste. Hide toolbar, full screen, resize, and we should be ready to roll. Alright, let's do this. We got about 17 minutes. We got this. Main, we have sorter. But we're not really ready. We have a lot to do on this first line. We're not really ready to do sort yet. I'll put the variable there, but we got a lot to do. So we have new insertion sort, which will be assigned to sorter. But before we can call that, we have to resolve its arguments, which is another method call. So we do have to do these in order here. Like for array lists, I don't have to do things in order or I can just do things left to right because there's no method calls, nothing really to resolve. Here we got a lot of work to do to resolve the argument, so we have to do this in the proper order. Inside the parentheses first. New int decreasing. So we have int decreasing, and it doesn't return into any variables, so no return arrow here. This, and I see the keyword new, so I am creating a new int decreasing. Constructor is int decreasing. And it takes no parameters. This was OX100. And I have to look at int decreasing, has no instance variables, extends comparator of integer, which also has no instance variables, and extends object, which will have no instance variables. So we actually have an object that's not going to have any instance variables, which is fine. That's allowed. That's legal. We can do that. So I have a object with no instance variables. And then we're ready to call the constructor. So I'm going to look in int decreasing, look for a constructor, and I don't find one. But no need to worry. We know that if we don't write a constructor, we get the default constructor. It has no parameters and an empty body. But wait, this class, and this is why I want to keep comparator as a class for this example, this class extends another class. If a class extends another class, what always, absolutely 100% of the time must always happen is the superconstructor call. That superconstructor call still happens. So the default constructor effectively has an empty body, but even an empty body still implicitly calls the superconstructor. So we have to call the comparator superconstructor again, because the superconstructor is always called. That's not optional. So we have a superconstructor call. We know this happens. We know it's still OX100, and we have to resolve this superconstructor. So we're going to look at comparator. So we're going to look in the comparator class for a constructor, and we also don't find one there. So we have a default constructor that is calling another default constructor. So we have a lot of invisible code here, but you'd still have to know that we get the default constructor. The superconstructor still has to be called. You see the keyword extends. You have a superconstructor call 100% of the time. So the superconstructor call still happens, but it is also the default constructor. So we still have two constructors on the stack. They don't really accomplish anything, but they still do exist and they still have to be traced. Now, again, just like a few other things I mentioned, I think that's a little bit too much of a trap question for an exam. But that is what happened. It's a good thing to show in lecture still, though. That's why I still want to show it. And all that still happens. Two constructor calls, even though neither of them have any actual code visible on screen. That still all absolutely happens. And then, so we resolve this. This resolves to OX100, and then we have our insertion sort. Insertion sort constructor, which does return to a variable, which has this is a keyword, which we need a new object. We get OX200. This is insertion sort. Map the constructor, and its argument is this new int decreasing, which resolved to OX100. So we have one parameter. Its argument is OX100, and we're calling the insertion sort constructor, which is going to take one parameter named comparator. And the insertion sort object has one instance variable also named comparator. And I don't see extends. I don't extend anything, so that's it. I don't have anything else to look at. Then we're going to call the constructor. This dot comparator equals comparator. And this returns OX200 back to the main method. Then we have an array list. Now, new array list, the constructor, and arrays.asList, this static method in the arrays class. This is all internal to Java, so you don't have to trace anything here, any method calls. You just have to know what the end result is. That will get list. We do see the keyword new, so we have a new array list on the heap. List is going to have a reference to that array list, and that array list is being initialized with 3 values at index 0, 1, and 2, getting the values 1, 6, and 7. You would have to know that all of that happens in this line of code, even though you don't have to trace. We're not going to make you trace all the method calls and everything. But you have to know this is the end result. Same with a few other Java built-in methods that we've come across, here and there. Adding to an array list, getting an array list size, hashmap.keys, things like that. You do have to know what some internal methods do. If you don't like that, well, I guess we can just have you trace them and give you all the code for them. That'd be so tedious. That'd be annoying. Be annoying for you to do and annoying to grade. And then the next line we have output. We don't know what it is yet. It's going to get the return of some method call to a method called sort. Returns to output. Sort is going to get a reference this. It's called through sorter. So sorter.sort this object of type insertion sort, which is OX200. And it's getting list, which is OX300. And we're looking for sort in the insertion sort class. Insertion sort right here. The input is called input. The parameter is called input. And then we're ready to roll with this thing. So we're ready to call this method. So first thing, output. And again, we just have to know that that's going to, new array list is going to create a new array list. I guess that one's pretty self-explanatory. New array list with no values. We got OX400. So output is OX400. We have a loop. This loop has a variable declared in it, so we do need our code block value to insert. And we're iterating over input. Input is 300, so we're going to start at value 1. So value to insert 1. We have location equals 0. This is declared inside of our for loop code block. So location equals 0. And we're going to count the elements in the output that come before the value we're looking to insert. Increment location each time, and then insert at that location. We didn't see this add method before, but this takes an index and the value you want to insert. And we'll insert this value at this index, and anything at or after that index is going to be pushed down by one index. So we're not setting. If you use set, you're replacing what's at that location. Here we're using add, which will preserve all of the information and add a new value to it. This loop does not execute at all because output is currently empty. So we don't even get a code block with value to compare. We don't get anything there. The whole loop is completely skipped, and we're going right to output.add. Output.add, we're adding to this array list at location, which is 0. Value to insert is 1. So we're going to insert at index 0 the value 1. We hit the end of our loop. So input is going to get, value to insert is going to get reassigned to the next value of input, which is 6. And then location equals 0. I know it's silly, but we will cross out the 0 and write a new 0. Technically, what's happening here is we're getting a brand new variable being declared. That's a little awkward to show in a memory diagram. And I think this is the first time it comes up, declaring a variable inside of a loop. We're going to just treat that as reassignment in the memory diagram. But technically what happens is we hit the end of the loop, location is removed from memory, and then we redeclare a new variable named location and initialize it to 0. For our memory diagrams, we'll just treat that as variable reassignment, or else things will get kind of messy. We used to do something different, and the memory diagrams were messy, and we stopped doing it that way. We would have a separate code block for each iteration of the loop. We would have one code block for, like a big code block for the iteration variable, and then a separate code block, or a separate dashed box at least, for all of the local variables declared inside of the for loop, and it's just kind of a mess. Okay, we hit our second for loop. Here we have a code block inside of a code block for the first time this semester, actually. Value to compare, which is iterating over the output. Output has just the value 1, so we have 1. And then we're going to ask our comparator what comes first. So we have comparator. Oh no. It's an important spot to have it to. This dot comparator. So we have this dot comparator dot compare. So we're calling compare from this object int of type int decreasing OX100. So we have compare is a new code, man, I'm saying the wrong one. A new stack frame. Stack frames cannot be nested. Code blocks can. Stack frames cannot. So this goes below everything that we're already creating. And this is OX100. And this is why it's important to still have int decreasing on the heap. Even though it has no state, it has no instance variables, we still have it so we can resolve method calls through inheritance, and we are using also polymorphism, but through inheritance to figure out the method call that's happening, so we can still figure out what's being called here. So we have compare. We're comparing two values, value to compare and value to insert. Value to compare is 1. Value to insert is 6. I don't know what the parameter names are yet. For that, we're going to go to compare from the int decreasing class. So we're going to go to int decreasing, look for a method called compare. I find it right here. It is overriding a method that was inherited, but the annotation, the override annotation, is optional. I do not have my annotation this time. That's perfectly fine. The progressions work the same way as it always does. In the memory diagrams, I don't even emphasize the annotation unless I want to talk about it as a side note. The annotation does not change your memory diagrams at all. If you don't see any override annotations in a trace on the midterm, you're still going to trace the same exact way as if they were all there. So we're calling this, my parameters are A and B. A and B. And I'm returning A greater than B. A greater than B is false. So this is false. So we do not increment location. That's the end of this code block. And then output.add. Output.add location is 0. So we're adding at index 0, we're adding value to insert, which is 6. So we're adding at index 0 the value 6, and that will push everything else down by 1 index. So 1 gets pushed down to index 1. So we have 6, 1 in our output array list at this point. We at the end of our outer loop, so input is, man, I did that again. Value to insert is going to be updated to the next value of the input list, which is 5. Location gets reassigned to 0 again. Yes, I know it sounds silly. I say reassigned, but redeclared and assigned. And then we have another inner loop. This time we did actually completely finish the loop and then got to it again. So there are 2 code blocks here that have to be created. Value to compare. By the way, this trace is pretty convoluted compared to what I would give you on an exam. If you can follow this one and trace through this one, you are doing great. Nested for loops, probably not necessary to test you on that in an exam setting. Output, which is now 6 and then 1, so this is going to get 6. And then call our comparator again. So we have compare. So if you are overwhelmed by this one, it's not the worst thing in the world. You should at least be able to follow as I go through this one, but being able to trace this on your own would probably be, I'd say that's a little beyond expectation. So value to compare, value to insert. Value to compare is 6. Value to insert is 5. By the way, definitely a side note, but if this course wasn't mastery based, if I didn't have the learning objectives and say you have to pass both learning objectives to pass the course, then this would absolutely be a fair exam question. Because then, like, oh, you got a 70 out of 100 on the exam, you know, whatever. You didn't get everything on the trace. But since it is, no, you have to demonstrate that you really understand what's going on with this trace, at least related to the learning objective. I got to hold back on the trick questions. So there's a reason why I keep saying that. And then it's A and B. A greater than B is true. So this returns true, which means we will increment location. We finally get location off of 0, gets to 1. Get to the end of the loop. value to compare is now 1. We're going to call our comparator again. Compare this OX100. We have A and B. This time its value to compare is 1. Value to insert is 5. 1 greater than 5 is false. So we do not increment location again, and we get the end of this loop. We have output dot add. Location is 1, so we're adding at index 1. We're going to add the value to add. Value to insert 5. Looking for the wrong thing. And then the add method will shove everything else down by 1 index, so 1 gets pushed down to index 2. We get our final output 6, 5, 1. That's the end of this loop. We iterated through everything in input 1, 6, 5, 1, 6, 5. So we're done with this loop. Finally cross out this code block. And then we're returning output, and we're done with the whole method. Output is OX400. I'm going to follow my return arrow. Output gets OX400. And the last thing to do with this trace is print that thing to the screen. And we're printing 6, 5, 1 to the screen. End of the main stack frame, end of the trace. That's our final trace, our final output. No, 2 minutes over, but we got there. We got to the end. So I'll hang out for a few seconds just to, so if you have questions, you have a chance to ask them. But that's the end of our lecture content. Don't forget the deadline. Oh, I'm in. Like, where's all my stuff? Because I'm already in the browser. Don't forget the deadline tonight. Important to hit these deadlines. Maximize your points. You can't miss too many points and still do well in the course. So definitely the problem sets are easier. That said, problem set 1, actually let me talk about it a little bit here. This last method, this resolve all collisions, this does get pretty tricky if you want to try to get all 15 points. It can be hard to do. At least grab the 5 points. I don't think it's too hard to get 5, but it's also really easy to write, probably what a lot of you are going through right now. It's really easy to write an infinite loop here. Think about all of your edge cases if you're hitting an infinite loop, or try to have some way to shortcut your method. So if you know the circles aren't moving, or maybe you're just wiggling them back and forth, so they're never resolving all the collisions, make sure you're adding some failsafe there so that your method still ends, that you break out of your loop instead of going infinite. One thing to really think of, the trickiest edge case, I'll spoil one of the edge cases right here for the hard resolve all collisions method, is 2 circles, different radii, but the same exact center. Most times where I see code going infinite, they're not handling that edge case at all. They're not handling that edge case. So make sure you're looking for that one if you're trying to resolve all collisions. You just want to get like the first 5 or maybe the first 10 points, but you keep going infinite and timing out in Autolab. That's one of the biggest things to look for. There's also the more common edge cases that you'll probably think of if you have 2 circles that are both on the x-axis or both on the y-axis. Maybe one's at the origin. Those edge cases I would expect you all to be thinking about and address that all in your code. But 2 circles with the same center is a little trickier. If you're really struggling with this one, at least comment out all your code for this one. Just have it do nothing, just absolutely do nothing, and at least get the first 35 points, and then start working on your infinite loops if you have that situation. Okay, and that gave time to ask questions about the lecture content. I don't see any questions. Must mean you're all good to go on all this stuff. And I'll see you all next Tuesday. Take care. See you then.